projector turned on and go over a few announcements. I think you've heard them all before, but let me just, well, one of these you may not have heard. There is a special presentation coming to the Birmingham East Campus Friday morning, 9:30. It's UAB's traveling group of singers. I can't remember how they call themselves. They're doing some of the Broadway hits, and that will be 9:30 Friday morning in the A.G. Gaston Auditorium. That's on the Birmingham East Campus. I think this is going to be quite a nice show, presentation. I highly recommend you try to consider going to that. I know I'm going to try to get over there if they don't have meetings or other things planned that are going to tie me up, but I'm going to try to be there, so it should be quite good. Now, we have a pretty good relationship with UAB, and I wouldn't be at all surprised if maybe some of our former students are over there as singers now. I don't know that for sure. I'm just making a guess, but it's take it back. Brian came in and took one of my markers. Characteristic mark. So anyway, if you can, that should be well worth the time. Friday morning, 9:30, A.G. Gaston Auditorium on the Birmingham East Campus. Okay, next, I talked about applications for graduation. If you're graduating this term, I hope it's in. Okay, if not, you better get it in. If you're graduating next term, this is the best time to initiate it. You can't get it all done yet, but you can at least get started on it, and that is start your degree, get your degree plan, get with your advisor, do a degree audit, see what you have taken, what you're taking now, and what you still have to take, and then when it's time to register for spring term, which hopefully would be within a few weeks. Usually we wait till first mini term's over with before we start registering for, we register for second mini term, and then after that gets going, then we register for spring term and summer if you choose. But then would be a good time to get with your advisor and make sure all the classes that you need are being offered. If they're not, you might be able to talk with department chairs or instructors and see if they can offer, if there is one more or two more classes you need. So that kind of stuff is good to get going the term before you graduate. So all of you are getting closer to graduation, so please plan to do that kind of stuff the term before you graduate. Don't wait till the term you're going to try to graduate. Okay, also note takers are needed for fall 2018. I don't know if they have all they need, but if you're willing to do that, please let Dr. Renee Herndon or Miss Janine Jones on the Birmingham campus know. The Space Center is looking for peer tutors in math, English, biology, computer science, and Spanish. Miss Leslie Hawker on the Birmingham campus, and can't think of the gentleman's name down on this campus, but it's down in room 105. Check and see if they need any tutors. All right, and then the one more thing. I had not anticipated going over as much stuff in Chapter 5 as what we're doing. I was just going to combine Chapter 4 tests and Chapter 5 tests together, and then when I saw how much there is to cover in Chapter 5, I decided I should have given you a Chapter 4 test. I already had it made out, but I didn't have it typed up. I got it typed up yesterday and forgot to take it to the copy room. I took it to the copy room this morning and found out the copier has been down since yesterday, so it probably wouldn't have made a difference if I'd have gotten it down there. Now, she said that he could be coming anytime, so before you leave today, let me run down to the copy room and see if they got it copied. If they do, fine. If they don't, I can run to the Financial Services office and they'll let me make up to 10 copies, maybe a couple more if anyone else comes in, and I can get enough copies made for you guys, and then we'll worry about the others later. Okay? So don't leave home without it. Don't leave here without the test. So you can, if you have time this weekend, you can start working on it. It's the Chapter 4 test, And it goes back to stuff that you probably say, I don't even remember doing that, but we did it. So anyway, stand by for that. Any questions on anything we've done so far? Okay, I'm sorry I didn't do the test for you earlier. I just thought, we'll just do a few things in chapter 5 and combine those with the test. 5 is drug on, and I thought, no, y'all need to had a score already, but didn't. Let me turn off the first slide. So it'll be a little easier to read this. And Clark needs his map anyway, so. Okay. All right. Any questions? Anything we've done up till now? All right, where we're starting now is differentiation and integration, which is what we've been doing all along, but now we're talking about with exponential functions, okay? Now, to differentiate exponential and logarithmic functions to other bases, you have 3 options, okay? You can use the definitions of a to the x and log a to the x, differentiate using the rules for natural exponential and logarithmic functions. That's the way I would go. I mean, it's so easy to do these. Why mess with the other? But you could also do logarithmic differentiation. We did that a little bit earlier. Or you could use the differentiation rules for bases other than e given in the next theorem. And we're just going to do sort of a slideshow on this because I don't know. If you find this is easier, go for it. This is differentiation, derivatives and bases other than e, the natural base. Let a be any positive real number except 1, okay? Because 1 to the x is always 1. So it's just not very interesting. And you can't do a negative number to the x because then it would have to be flip-flopping back and forth if x was an even number, then it just can't do it. So we only have positive real numbers except 1. Okay, we want to use 1. Then let u be a differential function of x. Okay? Then d to the x, I like saying that, of a to the x is log a times a to the x. That's it. Yeah, that's all. Derivative of the exponential is just log of the base, the natural log of the base times the exponential. The d to the x of a to the u would be log a again, a to the u, just like this, but now you have the du dx. Okay, that's a function of x. So it's just like this, only you add another term, du dx. Same thing here. When you're doing the log, the du dx of log base a of x is 1 over ln a times 1 over x. So remember, I mean, it's just the same derivative. Okay. If this was e to the x, it would just be e to the x. Since it's a to the x, you just put a log a in front. If this was a ln x, it would just be 1 over x. Since it's a log of a base other than e, okay, you just put la in front of the x. So that's downstairs where the x is. And if you're doing log of base a of u, it's the same thing, 1 over ln a, natural log of a, and 1 over u, so it's downstairs with it, and then you just du dx, whatever your u is a differential function of x, whatever that is. All right. Again, you can look these up if you forget them. I don't memorize them. If you have the opportunity to use them often, you'll probably remember them. But if you don't, look them up. Okay? And if it's okay, we'll just go on and not do these examples. Is that okay? I don't think I'll test you on the East. I don't intend to. Okay? But you want to do a couple of them just to see, or are you okay skimming over?
Let's do 1 or 2.
Huh?
Let's do 1 or 2.
Okay. Which one you want to do?
B and C.
Second?
What about B and C?
B and C. Okay. It says find the derivative of each function. Let me get my pen activated here. Okay. So you want, let's call it y prime. What would that be? log 2, natural log 2. Okay? All right, and here's Jordan. All right. Since you weren't here last time when we talked about this, and this morning yet when we talked about it again, let me just say it again for you. I had planned, we were just going to fly through a little bit in chapter 4. That took longer than I intended, but we only covered like 4 sections, I think it was. So I decided, actually it made out a test for chapter 4, but I thought, we're just going to do a little bit in chapter 5. Let's just go and combine those together. Chapter 5 turned out being a lot more than what I intended, and now I thought, well, y'all should have had a test already. So I've gone on and typed up the test for chapter 4, and I have it ready, but the copy machine's broken. So if it hasn't gotten fixed by the end of class, I'll make copies in the financial aid office. They'll let me do up to 10. And it's 2-page test, so that if it's just the 5 of you, I can get the 10 made, the 10 copies made. So, 2 pages, 5 each. So 5 of you. So don't leave without the test on chapter 4. I know it's a long time ago, but hopefully you remember it. All right, got the first part of it. Log 2, natural log of 2. What's next? 2 to the 3x, because that's just an exponential function. Okay, and then one more step. Chain rule. No. The derivative of 3x. 3. Okay, I'll put it in front. Okay? And you want to do C also? So what's y prime of that one? Help me. Anybody? Not natural log of cosine, natural log of 10, the base. Just like here, it's log 2, right? It's ln 10, not log 10, it's ln 10. Okay? That's the first part. Second, you certainly have a minus sine x in it. Okay? That's the derivative of cosine. And then your other part may have been okay. What did you say before, Clark?
Cosine x.
1 over cosine x. Did you say that before? Okay, yeah. I was looking for the log 10 first. But yeah, so 1 over cosine x is certainly true, but you also need the log 10 in front of it. But in the denominator also. Then, the derivative of the inside, chain rule, and that's your minus sine x. So it's minus sine x over. And another way you could write that, by the way, would be this. Minus 1 over log 10 times the tangent of x. Because sine of, not up there. I don't know how it got up there. Get down there where you belong. Okay. What's that? What was A? Oh, we didn't do that. We'll do it if you want me to. Okay? Do it. What's that y prime? Yeah, you start with natural log of 2 times 2x. 2 to the x. Yeah. The derivative of an exponential function is the exponential function, but if the base is other than e, then you have to put natural log of that base in front. Derivative of a log of a function is 1 over the function, but if it's a log other than base e, you put 1 over log of that base down there too. But if you've got an argument to the function, then you do the chain rule. you do the log of the, you do the derivative of whatever the function is. Make sense? Okay. What's that? Why are we using logs? That was what we're covering in chapter 5. What's that? Not all about. That's just the most recent part has been about. Well, this chapter, it's mostly about. This chapter is logarithmic, exponential, and other transcendental functions. So far, we've done logs and exponential. The others, not going to do too much with those. Okay. So anyway, that's what we did. Okay. This part, I'm planning not to test you on because we need to just move on. But I just wanted to show it to you while we were here on the thing. And he said, well, let's do a couple of them. Now we've done 3 of them. We want to do 4th one. It's up to you. Say again? Okay, what do y'all want to do? Yay or nay? Huh? Nay. Okay. I'll do to the next slide and let you see what they are. Y prime was that, log 2 to the x, just like we did. B was y prime of 2 to the 3x would be log 2, 2 to the 3x, then times the log of 3, which then bring the 3 log 2. That's your coefficient of the function 2 to the 3x. And the C part, the one we did too, was derivative of that would be 1 over log 10 cosine x times derivative of cosine x, which is minus sine x, which then you could write as minus 1 over log 10 tangent x, which I hope is what we did, right? Yeah, okay. Now, y'all chose not to do this one. I was sort of, yay, okay, because we didn't really want to. But it's not bad, okay? Because what you need to do before you start doing the quotient rule and the chain rule, that gets nasty. Use the properties of logarithms to make it easier. This is log base 3 of this minus log base 3 of that. So that's what they did here. Except that this is x to the 1/2, so log base 3 of this would be 1/2 log base 3 of x minus that. Okay? Now, you take your logs of this, the 1/2 is a coefficient. You have a 1 over ln of 3, that's your base, and a 1 over x. That's the first part. This part, a minus 1 over ln of 3 again, times ln of 1 over x plus 5. And there's no chain rule to do with that. Okay? So that's it. That's fairly much simply it. Use the properties of logarithm to help you make life easier. What's that? What about multiply? Yeah, you don't have to divide there. You just subtract the logs. Is that what you're saying? I couldn't hear. Okay, if they were multiplied together, you'd add the logs. Okay, that's the properties of logarithms. Okay, now the next step there would be derivative of that thing, then would be 1/2 or 1 over 2 log 3 1 over x. Okay, all that's in the denominator minus 1 over log 3 and 1 over x plus 5. And that's it. That's it. Not much way to make it any nicer that I can think of. Oh yeah, okay. Okay. What they did was, what did they do? Oh man, why would you do that? Okay, they got a least common denominator, which is 2 times log 3 times x times this. Okay, so that's what your least common denominator is. This one goes into this x plus 5 times, right? All that's the same. So it'd be an x plus 5 in the numerator here, minus, and this will go into that, a 2x times, minus 2x. So you have an x plus 5 minus 2x. That would be x minus 5. 5 minus x. Yeah, I would have loved to have done that. I don't know why they did it. that answer looks just as good, but if you wanted to simplify a little bit, that would have been fine too.
Where does the 1 come from on the right side?
Where?
On top, on the far side.
Okay. All right. Derivative of a log is 1 over, right? So that's for this one, right? And it's 1 over 2 that you already had there, log 3 that you pulled down here, and then 1 over x for there.
All right, I got you now.
And then the same thing here, it's a minus 1 over log 3, 1 over x plus 5. There is no chain rule of either one of those.
So the natural log is the derivative of it. I mean, that's how you write it when you've taken the derivative of log.
All right. Let's go back a few slides. I think it'll be on here. Here we go. No, that's not what I was thinking it was going to be. Let me see if it's. Here we go. This one. Okay. What log base A of x is 1 over log A times log x, natural log. So if you had done this, that's where the ln A, it goes downstairs, 1 over ln A. If it's, see if they have the other one with differential. Or, yeah, if you have a to the x, that's e to the ln A x. You can change from any other base to an exponential by putting the ln of the base in front. For an exponential and for a logarithm, where is it now? Come on. Was it this far? Yeah, there it is. To change that to ln, put 1 over ln A times ln A. So that's basically what you did. Anytime, so basically what you did was change it to a ln function, but not quite all the way. And for an exponential, that's just multiplied by ln A, and for a log, it divides by ln A. So that's where those came from. Right here. So it's an exponential, you just multiply by ln A. For a log, you divide by ln A. So that's how it got down there. Okay. I don't know if that answered your question or not, but it sounded like it might. Okay. So, all right, good deal. Now, they just carried it one more step. Okay. Now, first let me mark Vince here, and secondly, let me tell you what. I think if you were here at the end of class last time, I think I said, chapter 5 is stringing out too long. Let me go on and give you the test for chapter 4. I already had it made out, but I was just going to modify it and add a couple from chapter 5 to it. Since that's stringing out too much, I decided let me go on and make up the test for chapter 4. I already had it made up, I just hadn't typed it yet. So I typed it Monday afternoon and yesterday, finished typing it. And I meant to get it copied last night, and I was going to pick it up this morning. I forgot to take it down there. I was already driving home. I was I forgot to take my thing, and I was running late. So I took it down this morning, and the copier's down. But it was down yesterday, too, so I don't think I could have gotten it copied yesterday. The repairman's supposed to come out, but she doesn't know when. So if at the end of class that's not been copied yet, then I'll take it to financial aid office, and I think they'll let me do 2 extra pages. I'm supposed to keep it less than 10 pages there, but I'll make 12 pages because there's 6 of you here. It's a 2-page test. So don't leave until you Sorry I didn't get it done earlier. Didn't think this was going to take so long. All right. Occasionally, an integrand involves an exponential function to a base other than e, and we had already talked about that. When that occurs, there are two options. Convert to base e using the formula a to the x, is one I just showed you before, is equal to e to the ln x, okay, ln a x. Then integrate directly using the integration formula, okay? Now, and that's pretty straightforward to do. This becomes 1 over, where did that come from? Oh, I see what it is, okay. If you rewrite it like this, then it'll be e to the, you're integrating this thing instead, and that would be e to the ln a divided by ln a, okay? But e to the ln a is a to the x, so that's exactly what you get from it, okay? Plus c. So guess what? You can always look these up in a table. If you don't use them enough to remember them, look them up in a table, okay? And that follows from whatever theorem 513 was. Do you want to do this, or are you okay with it? What do you think?
I think we're okay.
Okay, all right. Here's how you do it. It's just 1 over ln2 times 2 to the x plus c. Okay. A lot like e to the x, okay, that would have just been e to the x. You just have the 1 over ln2. And the reason it's 1 over is it's an integration, so rather than multiply, you're dividing. Okay, it's inverse principle of differentiation. Okay, so here's a power rule for real exponents. D by dx of x to the n would just be n x to the n minus 1. So nothing new there. Okay, I'm not sure why they're going over this again. And d by dx of u to the n would be n times u to the n minus 1 times du dx. Nothing's changed there. We've done that forever, right? Nothing new here, okay? Something you've already done before. Okay? Now, this is bizarre. Okay? E raised to the e power I don't see how that could possibly be 0. Okay? This is example 5. No! That's supposed to be d by dx. Okay. D by dx of that. Okay? Now, why would that be 0? Because e is a number, 2.7 blah, 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 an irrational number. And that raised to a power, a number, is just a number. And derivative of a number is 0. Okay. So I said, no, there's no way e to the e is 0, but d by dx of e to the e is certainly 0. Okay? They've left it off on every one of these. That is true that e to the x is equal to e to the x. That's certainly true, but that's what they meant to do. They meant to do d by dx of e to the x is e to the x, which we already knew, right? And then the third one, did they mess that up too? Yes, they did. Okay? Yeah, in the book they got it right, but here they don't. Okay? So here, d by dx of e of x to the e. E's just a number, okay? Earlier we had the n there, but that's true. We're used to it being true for integers. It's true for any number. So this would be e times x to the e minus 1. The power rule. Nothing new there. except it's an irrational number. Both of them are. E is the irrational number. E minus 1 is an irrational number. Okay? Nothing new there. I don't know why they left off the d, but the x's here. Some sloppy graphics person, right? Okay. There is a d one here. Let's see what in the world they want to do. Oh, okay. Now, what if you had an expression like that? That's a weird number. I mean, that's a variable raised to a variable power. Well, anytime you have something like that, use your exponential and logarithmic things. So if this is an exponential, undo that with the logarithm. So take the log of both sides. Log of y is equal to log, and I always do natural logs, they're much easier to work with, x to the x, right? Would that not be true? Okay. Now, of course, you assume y is not 0 and y is not negative. If it was, can't do this. Okay. You wouldn't want to do it. But I think if x is positive, which I think it has to be, then that would never be negative anyway. Okay. X can't be 0. So, okay. Now, you can fix this a little bit more. Log y is equal to x log x, right? Now, if you are now going to differentiate it, which is not what they said they were going to do, but if you were going to take a derivative of this thing, then the derivative of log y would be 1 over y times y prime, right? Okay? And the derivative of that thing would be what? The right-hand side. Anybody? What rule would you use? Help me, help me. What does that mean? X log x.
Use the power rule.
Not power. It's a product. Product of two things. X times log x. So what would that be? Not 1 over log x, 1 over x. Derivative of log x is 1 over x, right? So you did the first times derivative of the second, right? Plus just log x. Because derivative of x is 1, right? Times log x. Okay? Well, what is x over x? 1. Okay? So what we have here is y prime is equal to 1 plus log x times y, right? If you multiply both sides by y. But what was y? Y prime would then be x to the x times 1 plus log x. Okay? All right. It's nothing to memorize it, but just get used to this is the procedure you use on things like that. Now, I sure don't want to do a second derivative of that, but you could, okay? The first term is going to be just like the other, and then you just have another term to mess with. So, hopefully they won't ask that. So, y prime would be x to the x times 1 plus log x. All right. Any questions? Oh, let's see how they did it in case they did it any differently. Okay. Log y would be log x raised to the x, which would be log y would be x log x. Then take a derivative, and that would be 1 over y times y prime is equal to x, 1 over x plus log x times 1, ln x times 1. So that would be y prime over y equal 1 plus log x. Multiply both sides by y, but then substitute back in what y is, x to the x, and there you have it. All right, any questions? All right, applications of exponential functions. I'm not going to do too much on this. I think it's just going to be a slideshow. So the amount of dollars, oh yeah, well, this is a pretty practical example here. Didn't know they were going to start with this. The amount of P dollars deposited in an account with an annual interest rate of R in decimal form. So if it's 4%, you put 0.04. Dream on, not having 4% anymore. Okay, like 0.5% or something like that. What is the balance in the account at the end of 1 year? So if this is, the answer depends on the number of times in the interest is compounding according to this formula. A is equal to the principal times 1 plus R over N raised to the N. So if this was compounded once a year, it would just be the principal plus the rate times the principal, because if this is 1, that's 1, nothing new. Yeah, that would be just simple interest formula. If it's compounded twice a year, there's a 2 here and a 2 there, it's going to be a little bit better. If it's compounded quarterly, you put a 4 here and a 4 there. If it's compounded monthly, you put a 12 here and a 12 there. Every one of these gets a little bit better than the previous one. If it's compounded daily, that's a miserable fraction, but it's 365 here and a 365 there. Gets a little bit better. But it's really awkward to do those calculations. Well, the simplest thing is to compound continuously. Well, that would seem like it would be almost impossible to do. But that leads, okay, and here's what they do. I wasn't looking at this. If you compounded once a year, $1,000 at 8%, 8% of 1,000 is 80. So at the end of the year, you'd have $1,080. If you compound it twice a year, you pick up another $1.60. Not a lot. Compounded 4 times a year, you pick up a little bit more, still not a lot, another 83 cents of that. Compounded monthly, you get another 57 cents. Okay. Whoa, big deal. Okay. If you compound it daily, you get another 28 cents. Okay. So it's not increasing much, but it is increasing a little bit. Okay. If you had compounded continuously, what you get, okay, now here's the theorem. The limit, and it's not just because of this compound, this is where we actually get it. The limit as x goes to infinity of 1 plus 1 over x raised to the x power, which was exactly what that parenthetical thing was. The limit of that, and what you do now is put least common denominator is x, so it's x plus 1 over x raised to the x. That is the definition of the number e. The limit of this as x goes to infinity is the number e. That looks so bizarre, so strange, that would be the case, but it is. That's where we get the number e. I think that's how Euler discovered it and named it after himself, or someone did it. Okay, that is your number e. So if you're compounding continuously, and here they show some of the numbers there. If you put x equal 10 here, you get 2.59, blah, blah, blah. You can do this on your calculator if you have time to do it. 100, you get 2.70. 1,000, 2.71. 10,000, 2.71815. 100,000, 2.71827. A million, 2.71828. And that's getting awfully close to E. Someone do E on your calculator. E to the 1 equal. And it keeps on decimal. And it doesn't repeat that. It only repeats it once and then goes up to other numbers. So it's not a repeating decimal, okay? So yeah, we are basically at E there, or awfully close to it, okay? So therefore, if you substitute that in and then do this, this is E to the R. That is the simplest formula. Why every bank doesn't use it. It's so simple. A is equal to B, E to the R. So if you went back and did our 8% interest, remember from the table, let's go back, whoops, too far. No, that's not it. There, 365, so if you did it daily, $1,883.28. If you did it with the E in there, 29 cents, you got an extra penny. Good for you, okay. But that's so much easier to do than all those other calculations. Just really straightforward. So this is continuous compounding. A penny more than compounding daily, but I'll take it, okay? You can't buy a penny piece of candy anymore, but if you could, you would have a piece of candy. Okay.
After several years, you can buy a piece of candy.
Yes, yeah, absolutely. Actually, after several years, it adds up more than just a penny, yeah. Okay. So compounded n times a year is that, compounded continuously is that. Would you rather use the second? I mean, even though the bank might have to pay a little bit more, it's so much easier to calculate, okay? So when you're in your big bucks, you know, needing to keep up with this kind of stuff, that's what you do. Okay, this is just an example, and you would plug it in. 2,500 at 5%. The numbers will be a little smaller than before, but about equivalent, okay? Oh, here's the solution. When it's quarterly, then it's 4 down there and 4 times 5 up there. 5 years. Okay, so this will show up a little bit better because you're doing this over 5 years. So it's not just for 1 year, which is what we were doing before, but for 5 years, you just multiply that exponent by the number of years. So that's going to give quite a different number. Okay? 3,000. Okay, you went from 2,500 to 3,200. Okay? Nice. Okay? Do it monthly, and you have a 12 in there, and that leads to 3,208.40. So how much do we increase there? 3,205. We picked up another $3 and some. Okay? Not a whole lot. If you do it continuously, let's see what we get. Look at that simple calculation. Well, there we go. You pick up another $2, almost $2, not quite. Okay? So it does improve a little bit. There, I could buy a piece of candy. Okay, with that $2. All right, any questions? Okay. That's it for 5.5, basis other than thing. Now, I'm not going to give you any assignments there, but you can work on anything that you choose to. Okay, but I feel like we do need to do the next, or at least part of the next section. Okay? So let me get out of this, because this is something we will be using soon and very soon, and you'll use it repeatedly. Okay? Have y'all hit L'Hopital's rule before at all? Okay. I figure we better hit this. Okay. Slideshow from current slide. Still doing logarithmic, exponential, and other transcendental functions. Here we're going to look at some indeterminate forms, which we're not going to spend too much time on. Well, yeah, we got a little bit, because this is how we use L'Hopital's rule. Recognize limits that produce indeterminate forms and apply L'Hopital's rule to evaluate the limit. So we didn't do this back when we did evaluating limits way early on. You might recognize it. Let's just see. Okay. Now, You know that 0 over n, where n is some number, is always 0. N over 0 is undefined. Any number over 0, undefined. But 0 over 0 wasn't quite undefined. It's indeterminate. Remember, that's where we did our derivatives based on that. Okay? Another indeterminate form is infinity over infinity. Now, sometimes that's definitely undefined. Other times it may have a limit. These are indeterminate because they do not guarantee that a limit exists, nor do they indicate what the limit is if one does exist. So when you encounter one of those indeterminate forms, you're tempted to write the expression using algebraic techniques. Okay? Sometimes that may work, a lot of times it won't. Okay? So here's an example of an indeterminate form. The limit is x approaches -1 of 2x squared minus 1 over x plus 1. Okay? Now, how would you approach that? If you try to plug it in, put in a -1. -1 squared is 1. 2 times 1 is 2 minus 2 is 0. If you stop there, you say the limit's 0. But if you go to the denominator and put in a -1, you get 0. 0, 0 is indeterminate. Okay. So what you probably would do, hopefully you would do, is say, let's see if we can factor this thing. And let me get my pen changed. Okay. You can factor out a 2, and that would be an x squared minus 1, right? But you can factor that to be, help me, x plus 1 times x minus 1. Okay, now when you have that over x plus 1, the x plus 1's go out, and that's where our 0 showed up in the denominator. And then you can plug in x equal -1. -1 times -1. -1 minus 1 is -2 times 2 is -4. So it does have a limit. Okay? Now, okay. Now, here's another one. X goes to 0, 3x squared, as x goes to infinity. 3x squared, we're blowing up big time. Doesn't matter if you subtract 1 from it or not. It's still way out there, okay? And the denominator's the same thing, 2x squared. That's outrageous, okay? Now, here's the technique that we usually use here, especially since these two maximum exponents are the same. Divide numerator and denominator by x squared. This will give you 3 minus 1 over x squared. This will be 2 plus 1 over x squared. Well, as x goes to infinity, x squared goes really big, but 1 over a really big number is going to 0. Okay, so that gives you 3 over 2, 3 halves. All right. So those are the techniques. If you have it going 0 over 0, try to factor, okay, and divide out things. If you have it going to infinity, divide by your culprit, the maximum exponent. But you got to do the same thing in the numerator and denominator. Okay? So it works all right. Okay? Now, before we go any further, I'm going to show you something. This is a trick, but the trick works. And I'm jumping ahead. Take your derivative of the numerator, what do you get? 4x, derivative of the denominator? Huh? I'm sorry. Derivative of the denominator is 1. Okay? over 1 is 4x. Now put a minus 1 in for x. 4 times minus 1 is minus 4.
You can do it to all of them?
Okay, only if it's a indeterminate form like this or like this. Let's try this one. This would be, what's the derivative of the numerator? 6x over 4x. If you let x go to infinity, you're still infinity over infinity. So do it again. Derivative of 6x is 6. Derivative of 4x is? And what's 6 over 4? 3 halves. Okay. I want to say L'Hopital discovered this. He didn't. He wrote it up. He was a student of, okay, we'll get back to that later. Let's go on. All right, occasionally you can extend these algebraic techniques to find limits of transcendental functions. For instance, this one here, you could also do this factors as e to the x plus 1 times e to the x minus 1. Those cancel out. And of course, when you put a 0 in here, this becomes a 1. 1 minus 1 is 0. That is a 1 minus 1 is 0. Indeterminate. But if you factor this, that would be e to the x plus 1 times e to the x minus 1. This is e to the x minus 1. There you go out. You have e to the x plus 1. And when you plug in a 0 there, that would be 1 plus 1 is 2. So that would be 2. Let's see if the other one works. Derivative of this would be of this. E to the 2x times 2. And this would be e to the x, right? Oh, don't be guessing. What's the derivative of e to the 2x? Okay. Any e function is going to be e to the 2x. It's e to itself, right? Derivative is itself. But then you have a chain rule here, which gives you a 2. Okay? Derivative of minus 1 is 0. Derivative of e to the x would be e to the x. Okay? Now you plug in a 0. This would be... Second? Well, okay. I don't know what you mean. No. Okay. Ooh, okay. Oh, it's in the different section. Sorry. No. If you turn back to 5.5, is that right? No, 5.4. Second? No, actually, go back to 5.4. Okay? On page 342. No, maybe that's not it either. Should be. What's 5.2? Yeah, here it is. On page 344. d by dx of e to the x is e to the x. That's why I love exponential functions. The derivative of e to the x is e to the x. The integral of e to the x is e to the x plus c. Okay? That's why I love exponential functions. Its derivative is itself. It's just really bizarre, but it's true. That's why we call it the natural base of our number system. The calculus works beautifully for that. Okay? Now, so that's why we could do that. You don't, no, you. See, x is a variable, it's not a number. What you just said works when it's a number. When it's a variable, you use different rules, and that's what the rule is. So this one, this is what we wind up with. Now we can take the limit of that as x approaches 0, and 2e to the 0 is 1. 2 times 1 is 2 over 1. So that's 2, and that's exactly what we got before. Okay? They got 2 here. By doing that part, we we got 2 by doing it that way. Okay. Now, not all indeterminate forms, however, can be evaluated by algebraic manipulation. This is often true when both the algebraic and transcendental functions are involved, and then you have troubles. For instance, this one, you can't do it. There's no way you can do an algebraic manipulation. You can factor this as e to the x plus 1 times e to the x minus 1. That doesn't help you with the x down here at all. But this is still indeterminate. This is 0 over 0. Okay? Now, rewriting that to this, you take the limit of this. I don't think you can you? Yeah. No. That blows up. So, no. You have a mess on your hand. A big, big mess. So, nothing else. Okay? So, what do? Give up? Quit? No. Of course, you could use technology to estimate the limit by graphing the function and doing that. That's using technology. And come up with a value there. It looks like the number 2, and it is. Okay. You could do it by exhaustion, picking numbers closer and closer and closer to 0, and from both sides it's going to 2. Yes, you could do that. Okay. Or you could use L'Hopital's rule. To find the limit illustrated in figure 523, what we just talked about, the theorem states that under certain conditions, the limit of a quotient f of x over g of x is determined by the limit of the quotient of the derivatives, which is what we were doing. Okay? Now, of course, they both have to be going to 0, or both of them going to infinity. It won't always work. Well, I mean, may wind up being there is no limit, but this is what you do. Now, it says to prove the theorem, which I'm really interested in doing, you can use a more general result called the extended mean value theorem, which is f and g are differentiable on an open interval a to b, continuous on the closed interval a to b, such that g prime of x is not 0 for any x in AB, open AB. Then there exists a point C in AB, open interval AB, such that f prime of C over f prime of g prime of C is f of b minus f of a over g of b minus g of a. Yeah, that you're doing it for the numerator mean value theorem and for the denominator, so the ratio should be the same. Not sure that does a lot for me, but I can see why they would say that. Here's what L'Hopital's rule is, okay, with all the caveats attached. F and G be functions that are differentiable on some open interval a, b containing the number c, except possibly at c itself, okay? Assume that g prime is not equal to 0 for all x's in that a and b, except possibly at c prime at c itself. If the limit of f of x over g of x as x approaches c produces an indeterminate form 0 over 0, then the limit as x approaches c of this, which is 0 over 0, is the same as the limit as x approaches c over f prime over g prime. Now, that g prime is not 0, okay, as x approaches c, or anywhere in the interval a to b, then this is what your limit is, provided that the limit on the right exists or is infinite. Now, if it is infinite, you might be able to try it again. This result also applies when the limit of f over g as x approaches c produces any one of the following indeterminate forms: infinity over infinity, minus infinity over infinity, infinity over minus infinity, or minus infinity over minus infinity, or 0 over 0. This will work for any of those, okay? That's L'Hopital's rule. And if this limit doesn't exist, the same as any of these, 0 over 0 or infinity over infinity, do it again, do another derivative of numerator and denominator. Okay. L'Hopital's rule can also be applied to one-sided limits. For instance, the limit is alpha of x divided by g of x as x approaches c from the right reduces an indeterminate form 0 over 0. Then you can just keep doing L'Hopital's rule from the right. If the limit exists or is infinite, you just keep trying. Okay. Now, they have a little blurb on L'Hopital. Named after the French mathematician Guillaume François Antoine de L'Hopital. Okay? He's credited with writing the first text on differential equations, which was a differential calculus, which was a pretty good feat itself in 1696, in which the rule publicly appeared. It was recently discovered that the rule and its proof were written in a letter from John Bernoulli to L'Hopital. I acknowledge that I owe very much to the bright minds of the Bernoulli brothers. I've made free use of their discoveries. In other words, we name it after him. He didn't come up with it. Okay? He actually, I think, was a student of one of these, John Bernoulli. I think that Johann Bernoulli. And as a student, he had written it to him. And then when he wrote his book, he put everything he had learned from them, including this. He did not come up with L'Hopital's rule, but because it showed up in his book, everybody calls it that. The Bernoullis were brilliant mathematicians, but not the nicest people. I think he went in a rage when it was named L'Hopital's rule, not Bernoulli's rule, and it never changed it. Huh? I don't know. Just everybody calls it L'Hopital's rule, so they continue. Just like everybody calls tissues Kleenex, even though it's maybe made by a different company. Kleenex is a company, it's a brand name, but because they were the first one that did it, we call them Kleenex. Now, same thing. All right, let's see. Can we evaluate this? The limit as x approaches 0 of e to the 2x minus 1 over x. What would be your first approach? Well, indeterminate. Okay? Undefined would be 7 over 0. That's undefined. You'll never get an answer. Okay? But 0 over 0 is indeterminate. And I think that does give you 0 over 0, right? When x is 0, 2 times 0 is 0. E to the 0 is 1. 1 minus 1 is 0 over 0. So that's indeterminate. Okay? So, let's do L'Hopital's rule. That would say that's the same as the limit as x approaches 0. Approach the same thing. What's the derivative of e to the 2x? E to the 2x. Anything else? Anything else? Chain rule? Times 2. Okay. Over, what's the derivative of x? 1. Okay. Now let's evaluate that one. And what do we get? X goes to 0. 2x is 0. E to the 0 is? E to the 0 is? 1 times 2 is 2. It does have a limit. Indeterminate in that form, but when you do L'Hopital's rule, take the derivative of both the numerator and the denominator, you get a non-indeterminate form, 2. Okay, so it does have the limit, and that's what we saw it was earlier through all those other means. Okay, pretty nifty tool to have. Okay. Okay. All right. Let's see how they do it. I think it's the same way. Solution. Because the direct substitution results in indeterminate form, then take the derivative of the numerator. Oh, no, they're just showing the limit of the numerator is 0, the limit of the denominator is 0, so that's the indeterminate form 0 over 0. Okay? But do L'Hopital's rule, the derivative of the numerator is 2e to the 2x, the derivative of the denominator is 1, and then when you take that limit as x approaches 0, you get 2 over 1, which is 2. All right. Now, and this is what we were saying before, another form of L'Hopital's rule states that if the limit of f of x over g of x as x approaches infinity or negative infinity produce an indeterminate form that's either 0 over 0 or infinity over infinity, then you use L'Hopital's rule there too. What's that? Yeah. Yeah, it's 2. Derivative of e to the 2x is 2e to the 2x. What's that? Derivative of x is 1. Take derivative of the numerator and derivative of the denominator separately, okay? And then when you evaluate this as x goes to 0, x goes to 0, 2 times 0 is 0, e to the 0 is 1, 2 times 1 is. Okay? Yeah, you take derivative of the numerator and derivative of the denominator separately. It's bizarre. You didn't think that would be true, but it does work. Okay. What's that? That's what I was thinking. I thought you had to have it in Cal 1, didn't you? When we were doing limits. I thought we introduced L'Hopital's rule. Huh? If you're doing a limit, yeah. Yeah. But we didn't want to show you that. Maybe we didn't do it there. Some books do and some don't. I guess this one didn't. Okay. Sometimes it's introduced earlier, but this is introducing it now. I thought they're making such a big deal about it. It must be the first time they introduced it. Huh? Okay. All right. So let's do this now when you have a 0, 0, or infinity over infinity, provided the limits exist. They may not, okay? So let's do that one. What happens as the limit as x approaches infinity of log x over x? What's log x becomes as x goes to infinity? Going to infinity, okay? Not going there as fast as x, but it's still going, okay? So this is infinity over infinity. What can you do with that? Well, you can do L'Hopital's rule. And what does that tell you? Be the limit as x goes to infinity of, what's the derivative of log x? Anybody? 1 over x. No, 1 over x. And derivative of x is 1. And what's the limit as x approaches infinity of 1 over x? Where's that going? Oh. Yeah. Getting closer and closer to 0. That going to 0. Because, do 1 over 10. That's 1/10. 1 over 100. 100. What's that? No, that's going to 0. That's what I should have put just equal, but that limit is heading towards 0. 1 over x is going to 0. I should have just put equal 0. Let's see what they put. I think that's what they do. Because direct substitution results in infinity over infinity. That doesn't work. Apply L'Hopital's rule, and you get 1 over x, and the limit of x approaches infinity of 1 over x is equal to 0. Not just going to, but equal to. So I should have left off. Okay, well, just think about it. 1 over 100 is 0.01, right? 1 over 1,000,000 is 0.000001. 1 over 15 million, you just get smaller and smaller and smaller and smaller and smaller. I mean, think about the graph of that. Okay, as you go on out here, and on out here, it's getting closer and closer and closer and closer to zero. Okay? Nowhere else for it to go. It never goes negative, it never reaches zero, but it limits to zero. Okay. All right. Okay. In addition to the forms O0, 0, and infinity over infinity, there are other indeterminate forms, such as 0 times infinity. Who wins on that one? Okay? Or 1 raised to the infinity, or infinity raised to the 0th, or 0 to the 0th, or infinity minus infinity. Goodness gracious, where do they come up with these things? For example, consider the following 4 limits that lead to indeterminate forms. Okay? What if you're doing the limit as x goes to 0, 1 over x times x? Well, guess what, folks? That would be infinity times 0. Well, you don't have to do anything fancy. Just x over x is 1. That limit is 1. Done. Okay? Or, written as x over x, take a derivative. 1 over 1, that limit is 1. So yeah, that was so easy you don't even have to do anything to it. 2 over that would be 2. 1 over e to the x times e to the x. Now that one, let's see what happens. Take L'Hopital's rule here. Root of this is 1. Root of this is e to the x, right? 1 over e to the x, that goes to infinity. If you think x is going to get large fast, e to the x is large even faster. So that's going to be 1 over an incredibly small number really quickly. That limit is 0. Okay? This one, however, 1 over x times e to the x, take its derivatives, e to the x over 1, as that goes to infinity, that limit is infinity. So not all limits will, L'Hopital's rule won't produce always a limit. That one has no limit. I hate for them to say the limit is infinity. Infinity is a limit, okay? It's going to go. These 3 have limits. That one does not. Okay? So, but doing L'Hopital's rule shows it to you. Okay. All right? Because each limit is different, it's clear that the form 0 times infinity is indeterminate in the sense it does not determine a value or even the existence of a limit. Basically, you attempt to convert each of those to 0, 0, or infinity over infinity so that L'Hopital's rule can be applied. Okay? So let's do this one. How would you suggest we approach that? What's that? Okay, how do you do that? What power? To 1/2. Exactly. That's exactly how I would proceed with this. Because if you try to just plug it in, e to the minus infinity, that's 1 over e to the infinity, that's going to 0. But infinity, square root of infinity, is infinity. It's going infinitely large, no stopping it. But you got half of it done. This is the same as the limit as x approaches infinity of what? You got the x to the 1/2. I like that idea. But what else can you do? Put the next one on the bottom over e to the x, right? Because e to the minus x is 1 over e to the x, right?
You couldn't have did negative e? Ain't no such thing?
Okay. I think you just made up a new rule for me. I don't, sure I know that. Okay. Okay, no. E to the, yeah, 7 to the minus 3 would be 1 over 7 cubed, right? Okay, well, the same thing. E is just a number, but it's being raised to the minus 7, minus x, that's 1 over e to the x. Okay, anytime you have a negative exponent, yeah, yeah, okay.
I was just asking because you do like negative e to the x.
No, that would be a totally different thing. Okay. Okay. No. What you may be thinking is a log rule, maybe. I don't know. Okay. But this, writing it this way, as x goes to infinity, that's going to infinity. As x goes to infinity, that's really going to infinity. I mean, that goes really fast. But they're both going to infinity. So then what could we do with that? Since it's of the form infinity over infinity, we can do whose rule? Yeah, L'Hopital. Okay. And what's the derivative of x to the 1/2? 1/2 x to the negative 1/2. Okay. And what's the derivative of e to the x? E to the x. All right. Now,
So can you put both of them over 1 and just multiply?
what's that again?
1/2 x times e over 1. I mean, under 1.
Okay. I'm not hearing clearly what you're saying. You may be saying it right. I just don't know.
1 over 1/2 x times e x.
Okay. So in other words, move everything to the denominator.
Yeah.
Okay. That, I think, will work for you. Because you see you have 1 up here, you have a 2x to the 1/2, just like we did before, e to the x. Is that what you're suggesting? Absolutely. That's perfectly fine to do. Now, what happens here? As x goes to infinity, that's going to infinity, that's going to infinity, and 1 over infinity is going to 0. Right? 1 over a very, 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 very big number is going closer and closer to 0. So that's your limit. That's 0. Now, I don't suggest you bank on this all the time, but at least this gives me a good feeling for it. Especially when you do this, when you had it this. X to the 1/2, that's going to infinity like this. It's going to infinity, but it's going awfully slowly. You know, it's half a parabola sleeping, right? Okay, so it's still going. Whereas e to the x is point like that. Okay, so if you put this number down here over that and way up there, that's going to 0. Okay, every pair of them, they get further and further apart. You know, so that's going to 0. That's how I think about it, and it gives me a warm and fuzzy to see that's what it turns out to be. Okay, so let's see what they do. Because of the direct substitution, it produces the form of 0 times infinity. Try to rewrite it in that form, which is exactly what you did. Square root of x over e to the x, except we did x to the 1/2, because it's easier to take a derivative of x to the 1/2 than it is square root of x. And that gives you 1 over 2x to the 1/2, which is exactly what we had. 1/2 times x to the minus 1/2, which puts it downstairs. And then that puts everything downstairs. And then as you let x go to infinity, you have 2 times infinity. Big infinity, that's going to be infinity. And 1 over infinity is 0. Okay? Make sense? All right. Now, that was example 2. How many? 10. Okay. Let's see what we can do. Are you trying to get me to go down and look for the test now? Oh, yeah, I thought that's what you wanted. Are you in a big rush? Okay. I mean, does anyone have something immediate? You got to leave class immediately when it's over, or you have time for me to go downstairs? Okay, let's go and try to get it in. All right. The indeterminate forms 1 to the infinity, 0 to infinity to the 0, 0 to the 0, and 0 to the 0. Those are the same things, aren't they? Whoever did this slide, no, I think that last one's supposed to be infinity minus infinity. That's what it is in the book. But they've skipped example 3, so let's back up and do example 3. We'll come back and pick this up later. So let's do example 3, okay? Is it 3? 5? No. Wait a minute. All right, I'm getting a bit confused here. The one we just did, oh, we already skipped to example 4. We skipped example 2 and 3. That's what we did, wasn't it?
We skipped 3. We did 2.
No, we did 2, but we skipped 3. Sorry. Let's go back and get 3. Where will we get 3? All right. Let me erase this. All right. Let's do example 3. Evaluate this. The limit as x approaches negative infinity of x squared over e to the minus x.
Would you want to bring e upstairs to get rid of the negative x there?
Well, let's first see what we're dealing with here, okay? If you put in minus infinity there, well, minus infinity squared is still going to be infinity, okay? And e to the minus infinity will be e to the infinity. That will be infinity. So we have a form here that's infinity over infinity. So we already have a form we're okay with. L'Hopital's rule will apply to this. So let's not mess with it and mess up the possibility of L'Hopital's rule. Let's use L'Hopital's rule on that. And what would that give you? Numerator, take the derivative, you get 2x. Take the derivative of the denominator, you get, say again, e to the negative x times a negative 1, chain rule, right? Okay. Now, let x goes to negative infinity. The numerator would be going to minus infinity, and the denominator would be going to
Positive. No, it'd be going positive.
wait a minute. I said something. Oh, wait. Okay. It'd be going to minus infinity too, because minus infinity would be infinity, and e and minus that would be minus infinity. So that's still minus infinity. So let's do it again. Didn't help us a lot, but let's try it one more time. L'Hopital's rule again. That'd be the limit as x goes to negative infinity. And what's the derivative of 2x? 2 over 2 over.
So that'd be positive e to the negative x.
Yes, e to the minus x. Okay? Now we take that limit and you get 2 over infinity. And what's 2 over infinity? What does that go to? 0, exactly. Any constant to, yeah. So that limit is equal to 0. Yes, and that's what they got to. All right. Then we did example 4. Okay, say this one more time. Of what?
Negative E, negative H.
I can't hear you, sorry.
The negative E, negative H.
Negative e to the minus x?
That's the derivative of E to the negative H.
Yeah, that's derivative of e to the negative x.
I thought you said it wasn't such thing.
Okay.
I thought you said you couldn't do it.
No, I think what you, were you doing a derivative before? I didn't know you were doing a derivative. I thought you said, isn't that the same as?
Oh no, I was.
Oh, you were doing a derivative. I'm sorry. I didn't know you were doing a derivative. I thought you were simplifying it. And I thought, how could that be? Yeah, I got it. Sorry. If you're doing a derivative, that is correct. Because derivative of this is that, times the chain rule will give you a negative one. So yeah, that is correct. I'm sorry, I didn't understand. My hearing is terrible, so. Yeah. Okay. So that was example 3. We've already done example 4. Okay. And how are we doing on time? Huh?
4 minutes.
4 minutes. Okay. There's example 4. I just got lost because I skipped something. Okay. Okay. Here was the thing. No. This, they just put 2 and 0 to the 0th power. Okay. Okay. Now this sentence is the sentence that's the paragraph right above example 5, the indeterminate form, blah, blah, blah. They just put 2 and 0 to the 0th in there. Okay. Arise from limits of functions that have variable bases and variable exponents. Okay. All right. I don't like the forms. They're confusing, but let's look at the example. I don't know if we have time for it. Let's see. Here's example 5. Evaluate. Do we have time? Let's try. If we don't get it done, we'll come back. Evaluate the limit as x approaches infinity of 1 plus 1 over x to the x. Boy, that looks awfully close to an e to me, doesn't it? When we were doing this before, I thought that's what we turned out being an e. Let's see if it does. Well, let's see. Here we have, as x goes to infinity, 1 over x is going to 0, right? So this would be 1 going to infinity. Yeah, what in the world is that? Okay. Well, there's a couple of approaches you might want to take. One of these might be simplifying algebraically what we've got here, the limit as x approaches infinity of x plus 1 over x raised to x. Isn't that the same? Okay, that's the same thing, right? Now, you could write that as the limit as x approaches infinity of x plus 1 to the x over x to the x. I mean, it's getting a little crazy here, but that's what it is. And this is just infinity over infinity, right? This is infinity raised to infinity. This is infinity raised to infinity. So both of those are indeterminate forms. Very indeterminate forms. Okay? Now what might we try?
Leopold's rule.
Good old Leopold, huh? Okay. This is messy, totally messy. And what the book did, the reason I was heading this way is to show you it was messy and then give you an option for how to clean up the mess. But the book decided to clean that up at the very beginning, okay? So I'm going to back off of what I'm doing, and since we probably use most of our time, I think we'll just start there next time, because we don't have much time left, do we? Yeah. Okay, we'll start with example 5 next time, and I won't go into as much trying to convince you what to do. Okay, let's just look ahead. In 5.6, you can do some of the homework exercises here. You can do 3 and 5 if you want to using the tables, okay? And then it says using 2 methods. I would say use L'Hopital's rules, 7 through 13, and all those are at Calc Chat. And by the way, 3 and 5 are at Calc Chat also. 7 through 13 are at Calc Chat, 7's at Calc View, and then you could also do any of the odds 15 to 41. There's a whole bunch of those there, and 41 might be a little challenging, but all of those are at Calc Chat, 29's at Calc View. And I think the others, 43 to 51, same thing, 51's at Calc View. Oh, I'm sorry, it goes to 61. So do as many of those as you want. Some of them might be a bit heavy. I'm going to shut